So we're approaching the end of our Differential Calculus 1 playlist, and we're going to finish this off with solving optimization problems. And so optimization is a concept in Calculus 1 that oftentimes confuses a lot of IB and AP Calculus students, not really because of the calculus, more so because of just kind of interpreting the problem and creating a model or creating a function which models the problem. So optimization is really just kind of maximizing or minimizing functions in certain contexts. And so here is a very common example you'll see. So suppose we have an open-topped box that has a volume of 32 units cubed with a square base and a height h. And so essentially what they're asking us to do in this problem is to find the minimum surface area of the box, right? So we're trying to minimize the surface area of this box. And what we're going to try to do is we're going to try to kind of construct a function which models the surface area of the box as a function of the length or the length of the base of the box, right? And so then what we're going to do is we're going to try to minimize that function, of course, as they're asking us. So we're going to just use our principles from differential calculus using critical points in order to minimize our function. And so let's actually go ahead and do that. And so the first thing we can do is we can think about the volume of this function. I drew out a little model over here to kind of show what we're dealing with over here. So we have a box with a square base and its length is going to be x. We just denote it by x, and then we have a height h, and it's open topped. So we're not really going to be considering the area of the kind of top of the box when we're thinking about the total surface area. And so what we can do is we can go ahead and describe the volume right over here. We know that the volume is going to basically just be the base area times the height of the box, right? So x squared, that's the base area because it's a square base, and then times the height of the box. And we know that that volume is going to be equal to 32 cubic units. And so we can solve for the height in terms of x, right? So we can get kind of a function of x. We can get h is equal to 32 over x squared. And we're going to see why we need this in a moment. And so now we have the height in terms of the length of the base. Now we can think about the surface area, right? So the surface area over here, we know is just going to be the sum of each area of the face, or the sum of the area of each face of this box over here. And so the base face, kind of the one at the bottom, is going to have an area of x squared. And then we can think about each of these individual faces. So we're going to have this first face right over here. We have another one here, a third one, and then a fourth one over here. And keep in mind that we're not including the area of the top of the box because it's an open-topped box, right? And so we have four faces to consider over here. And each one is going to have an area of x times h, right? Because we know it's just going to be the base times height, so x times h. And we have four of them, so it's going to be plus 4xh. Keep in mind that we described h in terms of x, and we want this to be a pure function of x. We want it to be s of x, so the surface area as a function of the base length. And so we can go ahead and substitute this right over here in for our h. And so we get plus 4x times 32 over x squared, which is going to be equal to x squared plus, this is going to be what, 128 over x. And that is the surface area as a function of x. Now what we can go ahead and do is take the derivative, right? Because we want to minimize this function. We want to find its global minimum. And so let's go ahead and do that. So we can take s prime of x, which is going to be equal to 2x minus 128 over x squared. If you don't know how I obtained that, then I encourage you to review the derivative rules. And then what we're going to do is we're going to just think about the critical points over here. So we know that the critical points are going to occur when the function is equal to 0, or when, rather, the derivative of the function is equal to 0, or when the derivative is undefined, but the function is defined. We know that we're going to be undefined. We know that s prime is going to be undefined at x is equal to 0. But so is s. We know that s is also undefined because we're dividing by 0 in s, and we're dividing by 0 in s prime when we take x equals 0. So we know that x equals 0 is not a candidate for our critical point. So now what we can do is we can go ahead and think about when s prime is equal to 0, and that will be the critical points that we will consider. And so we can set s prime equal to 0, which is going to be equal to 2x minus 128 over x squared. We can go ahead and multiply everything by x squared because, x is not equal to 0 in this case. We end up with 2x cubed minus 128 is equal to 0. And then we can just solve for x, right? So we'll end up with x cubed is equal to 64, which tells us that x is equal to 4. And now we just need to make sure that this is actually a minimum, right? And so we can go ahead and draw our little number line in. Okay, I don't know why that didn't work out. So that's going to be our little number line. We can mark our critical point, and then we can think about values that are less than 4 and then values that are greater than 4, and then we can determine the sign of f, or s prime in this case. So s prime, if we can take, for example, 1, is going to be 2 minus 128, which is a negative number. So we know that s prime is going to be negative over this interval. And then we can think about maybe s prime of 5, let's say, which will be 10 minus 128 over 25, which is going to be 250 over 25 minus 128 over 25, which is just going to be a positive number. And so we know that s prime is positive over here. And so s is going to be decreasing over this interval. It reaches 4, it's stationary at that point, it has its minimum, and then it starts increasing. And so we go from decreasing critical point to increasing. We know that x equals 4. This is going to be a minimum, right? And so we have the length, which will minimize the surface area. Now let's go ahead and actually determine what the minimum surface area is of this box. And so let's go ahead and input x equals 4. So s of 4 into our function right over here. So that's going to be 16 plus 128 over 4, which is just going to be 16 plus 32, which is going to be 48 units squared, right? Because it's a surface area. And so that would be our final answer right over there. And so essentially, what we've noticed is that we can just use our principles of calculus. And the most difficult thing really in optimization problems is just getting that initial model, knowing where to start, knowing how to describe everything in terms of one variable, because a lot of times it's a lot easier to just describe things in terms of multiple variables. But here, whenever you can, use the information given in order to describe everything in one variable, and then use that model in order to determine what the question is asking for.